Hello everyone, my name is Jan and this is my Emergence Project. It's around this time of the year that you start to see birds fly south for the winter. They all seem to automatically know exactly where to fly, but how do they do this? You might think that they have an internal compass, a sixth sense, but it's actually a lot more complicated than this. Scientists have noticed that migrating birds' navigation abilities only work in the light and that they can't navigate nearly as well at nighttime. It turns out that there are two methods they use for navigation: seeing the magnetic field and using celestial clues when their magnetic vision is not as reliable. Look at this image of Earth's magnetic field. Normal human compasses work by aligning the north and south magnets to the north and south poles, letting us know which way is north and south. However, birds' magnetic senses actually show them the inclination or slope of the lines that make up a magnetic field. For example, if they're in the north and know that they should fly south, they will fly in the direction of the rising slope of the magnetic field lines. This kind of compass is called an inclination compass. Now that we know that they can tell north and south apart, but we don't know how they know where to fly in the first place. We're actually going to learn about this in episode 2 of this series. The bird's property of seeing Earth's magnetic field is called an emergent property. An emergent property is a property that evolves and works based on the unexpected combination of many parts in a system. This property goes on to let the organism do something that it was not previously able to do. Now, let's understand the system that lets birds see the magnetic field better by building up, starting with the smallest parts. The smallest part of the migratory bird's inclination compass is the CRY4 protein, a protein in the photolysed/cryptochrome family of proteins. When this protein is exposed to blue light, it becomes more sensitive and receptive to Earth's geomagnetic field. Therefore, when the CRY4 protein is exposed to blue light, it changes and informs the bird about where the magnetic field lines are and what they look like. Without the CRY4 protein, the birds wouldn't be able to detect the magnetic field at all. The next level is the cell. The CRY4 proteins are located in the bird's cone photoreceptor cells, basically their eye cells. These cells normally react to visible light that enters their eyes and lets them see normally. With the addition of the CRY4 protein to these cone photoreceptor cells, the birds are now able to see Earth's geomagnetic field as well, as long as blue light enters their eyes and excites the CRY4 proteins. Without the cone cells, the bird wouldn't be able to gather any light at all. The tissue that these cone photoreceptor cells make up is the retinal tissue, a type of nervous tissue. The retina is the part of the eye that receives and senses light, so many cone cells make up the retina. So, light information can be passed on to the brain to be interpreted. Without the retina, the light coming into the eyes wouldn't have anywhere to go. The organ that the retina is in is the eyes. The retina is part of the eyes of a bird, so a bird is able to get the light photons from its environment and respond accordingly. Without the eyes, the bird wouldn't be able to see anything at all. The organ system that the eyes are a part of is the nervous system. The nervous system in birds is the system that gathers information and sends it to the brain, so the brain can take action if needed. For instance, the bird's eyes collect information about the slope of the magnetic field lines, and the brain then figures out which way to fly. All parts of this organ system are necessary for the bird to navigate while migrating. Without the nervous system, the birds wouldn't be able to sense or react to anything. Based on the information about the system that this ability is a part of, we can now see that this is, in fact, an emergent property, because it is a combination of the light-sensitive CRY4 proteins, the eyes that let the lights into the proteins and gathers the signals, the brain that interprets the signals from the eye. Also, the birds are able to see Earth's magnetic field. Okay, so now we know exactly how the CRY4 protein allows birds to see Earth's magnetic field. But how did this emergent property evolve? To understand how this property might have evolved, we first need to learn about another protein in the photolysed/cryptochrome protein family, the flavin adenine dinucleotide FAD molecule. This molecule is very similar to the CRY4 protein, and the FAD molecule is commonly found in birds and reptiles. The purpose of the FAD molecule is to repair DNA that is damaged by UV light. If you want to learn more about the FAD molecule, stay tuned for episode 3. Most scientists agree that the CRY4 protein mutated from the DNA for the FAD molecule because of their similarities. But what benefits did birds gain from the emergence of the CRY4 protein? The CRY4 protein allowed them to navigate a lot more accurately because celestial clues are always moving and they're often obscured by clouds. The first birds who evolved this trait of being able to see the magnetic field of the Earth were likely able to migrate much faster, saving time and energy. To summarize, birds were able to know where to go when migrating due to the CRY4 protein in their eyes that let them see Earth's magnetic field, and when that doesn't work, they use celestial clues to navigate. This system that includes the CRY4 protein reacting to light and magnetic fields, all feeding to the brain that processes information, is an emergent property that allows migratory birds to navigate while migrating. Thanks for watching. Come back on February 30th for the rest of this series. Bye!